There's one small thing that I should have mentioned in the last class but forgot to, and it's this. Uh, we have talked about the eigenvalues and eigenvectors of u and c, and we found that if the eigenvectors of u are n alpha hat and the eigenvalues are lambda alpha, then the eigenvectors of c are the same, that is n alpha hat, and the eigenvalues are lambda alpha square. Now, these lambda alphas are called the principal stretches. Principal stretches because we have seen that when we divide f, when we split f into r times u, we actually split it into a pure rotation and a pure stretch. So these are called principal stretches. Lambda alpha are called principal stretches, and once you have expressed once you have found the eigenvalues and eigenvectors of u or c, then you can write them write the tensors C, for example, as in its eigenspace as in a spectral decomposition. So you can write C as lambda alpha square n alpha, which means there's no summation involved here. So this is lambda 1 square n1 square n1 square n1 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 dyadic n1 plus lambda 2 square n1 n2 dyadic n2 and so on. So here we express the tensor itself, in this case C, in terms of its eigenvectors and eigenvalues, and in this eigenspace C will turn out to be the matrix representation of C would be diagonal matrix. So the matrix representation of C in the space n1 n2 n3, which is, by the way, orthonormal space, will be simply this. So now we will deal with rates of deformation, or time rates of change of the deformation measures that we have learned so far. So the deformation measures that we have learned are things like F. F is a measure of deformation that includes both the motion as well, both the deformation as well as any rotation that might be imposed on a body. Then we have talked about C, then we have talked about E, then we have talked about the Almansi strain, and so on and so forth. We have talked about U, which is square root of C. So all these are deformation measures, and the rates of these deformation measures are also important. To look at the rates, we will first define a velocity gradient tensor, which we will call L, which is the spatial derivative of the velocity vector. So velocity is expressed as a function of small x and t. So this is a spatial quantity, and the spatial derivative of this is called L. What it physically means is that if this is the deformed body, which we have called omega, then at a point small x, the velocity vector v is this, and the gradient of this, spatial gradient of this velocity vector. So if I write it in initial notation, Lij is this, and therefore dvi is Lik dxk. So this, the rate of change of the change in velocity if you move by a small distance from dx. So if I move from here to x plus dx, where this distance is dx, the velocity vector is v plus dv, and this rate of change, this quantity dv, as a mapping of dx is given by L. So L tells me that if I move by a small distance dx, how much does the velocity of the point in the deformed configuration change by? Now we know that if we have any spatial quantity, we and if we want to find the total derivative of v with respect to time, we have to consider the fact that not only is this explicitly a function of time, but x itself is also implicitly dependent on time. Therefore, acceleration, which is the total derivative of v, will be written as del v del t plus del v del x into del x del t, which itself is v. So this is del v del t plus gradient of v, spatial gradient of v times v. So we can do this in indicial notation also. So I can write ai is del vi del t plus this quantity, which is del v I del xk into del xk del t, which is del vi del t plus vk, but del vi del xk from this definition is lik. So the acceleration can be expressed in terms of the velocity gradient, and it becomes del vi del x del vi del t like a vk. So this is the acceleration at a point. Now, several other quantities, several other rates can actually be expressed in terms of this very important tensor, which is the velocity gradient tensor. For example, these are some important results. Let us take the case of f, which we know is fij eij. We can write it like this, and fij is del small xi del capital xj ei ej. Now note that this small xi is a function of capital Xi and t. So capital Xi is not explicitly a function of t, which means that df dt, the total derivative of f, is the same as the partial derivative of f, which means this is equal to del x t of del xi del capital Xj, which is the same as del vi del capital Xj. Now we know vi can be treated as a function, as a spatial quantity. So these are functions of small x and t, and when we take del xj, we can write it as del vi del small xm del capital Xj using the chain rule. Del vi del small xm is lim, and del xm del x capital J is fmj, which means that df dt is, sorry, I shouldn't have written this. This is del fij del t. So this is the way. So this equal to is not here. So del f del t is simply lf. So what we write is f dot is equal to lf. Whenever we have del f del t kind of quantity, del t kind of quantity, we write it as f dot. F dot will denote a total time derivative. Okay. Now f inverse is easy. So if you want to find f inverse, you have f dot. So if you want f inverse dot, then you use the fact that f inverse is equal to I. Take derivatives of both sides, time derivatives of both sides. On the left you have f dot f inverse plus f inverse dot. This is I, so this is equal to 0. F dot is LF. So LF f inverse plus f inverse dot is equal to 0. which implies that L minus L is equal to F inverse dot, and F inverse dot is minus L minus F inverse L. So this proves this relation. So F inverse dot is equal to minus F inverse into L. Now let's get to the third. To prove this, we will have to use a result which I'm not going to prove. But if you are interested in a proof of this, you can look at Holzapfel, which is a book on nonlinear solid mechanics. The first chapter of this is a proof of this. So this is an important result, that the derivative of determinant of a tensor with respect to the tensor itself is determinant of the tensor times the tensor minus transpose. So using this result, we can prove the third important result that we have. We take the derivative of J, which is the derivative of determinant of F, which means that this det F is of course a function of F, so we can write it as del of det F del F we write del t instead of ddt because ddt of F and del t of F are the same things. Now we have this in between because on the left we have a scalar, so this side should also be a scalar. Now this is derived from this result, so this would be equal to JF minus transpose, and then this is, we have already found, L times F. Okay. Now let us look at this quantity. This quantity, if you write it in initial notation, you have to write F minus inverse Ji times L I M F M J. That is what you will have to write. The ij, the components of this, not the components of this, this quantity, the scalar quantity will be this. Everything is a repeated index here. And now Fji, and so you can write Lim Fmj Fji inverse, but these two together, inverse of each other, so these will give you delta Mj, no sorry, delta Mi, which is the same as delta Im. So you have Lim delta Im, which is Lkk. So you have this equal to J times trace of L, which is also J times Vk comma k. Okay, so that proves these three results, and these are very important results, so I suggest that you prove them yourself as well and make sure that you understand what these mean.